Hey guys, I'm Hannah Oppenheimer, and this video is going to be about cloaking devices. Remember those cool covers on our elementary school agenda books that change pictures when you move angles? Or those bookmarks that do the same thing? Those are fantastic optical illusions that focus on using angle changes to depict multiple images in the same space. These images are called lenticular prints, and they can combine up to 3 images in one. If you look at the print at eye level, you can see that it's made of triangular segments placed equidistant from each other. On the 2 surface faces, 2 images are printed, with the same one on each parallel face. In the spaces between triangles, 1 additional picture is printed, so that when you move to the left, you see the image on the left. When you move to the right, you only see a different image that's on the right. And when you're looking down the center, you see a completely different image than the first 2. But it's all in one picture. So this optical illusion is simple, but it's the basic foundation of modern cloaking devices. Optical illusions are things that deceive the eye by appearing to be something other than what it is. Another one of my favorite optical illusions is the mirror maze, commonly seen in like fun houses at the beach and such. So what happens is you look in the mirror and you see yourself, but there's multiple mirrors that make you unable to tell where there's an opening because the light is reflected across so many surfaces. If you take a step, you might bash your nose into solid glass, or you might press your hand up to a surface only to find out that the mirror that you thought was right in front of you is actually several steps ahead of you. The image that you see is actually a clever trick that causes confusion simply by toying with the angles of light. There might not actually be a mirror there, but you see a reflection solely because there's so many there that your brain just thinks, well, there might as well be one there too. Your brain naturally fills in the blanks where information is missing. If you take a look at this image, most likely you can still read it. The first and last letters of the words remain, but the middle is switched up. Your mind knows these words and can therefore summarize the overall meaning of the phrase. This can be applied to cloaking too, although total coverage is nearly impossible. Let's say you're looking at a forest and you see a slight movement, but you think nothing of it because your brain's like, oh, it's just the wind rippling the leaves. In reality, though, if you were to take a picture of the exact scene, you might notice that the shape is indeed a human shape. Blame your overreactive brain for this mishap. The same goes for the opposite effect. That spooky curtain might look like someone is hiding behind it, simply because you think you can see the outline of a head and maybe a hand. This illusion of light is incredibly diverse, and scientists have an advantage because the brain's always trying to fill in the blanks. In terms of cloaking devices, light is the key to successfully hiding an object. The main problem that scientists face is that when you change angles, like while looking at a lenticular print, the image changes and another source becomes visible. Many cloaking designs work fine when you look at an object straight on, but if you move your viewpoint even a little, the object becomes visible. I'm sure you're all thinking that cloaking is just confusing the naked eye, but actually, cloaking can be used to manipulate all types of waves on the electromagnetic spectrum, even ones we can't see. Other types of wave include microwaves, radio waves, infrared, which can all be manipulated with cloaking technology. Just like seeing requires light bouncing off an object and passing into your eyeball, things like radar can't detect a plane without radio waves bouncing back to a receiver. Airplanes use a form of cloaking when they use stealth mode, which is commonly used in the military. The goals of stealth mode are to reduce radio, thermal, and microwave emissions while also absorbing them. Several types of construction mechanisms can be used to perform this task. Granted, there are other principles of stealth mode like not opening any doors which would emit visible light, but the basics are the same as cloaking. In order to scramble radiation, pyramid-like shapes are fashioned to bounce the waves around until they decrease and become less detectable. Stealth mode does not make an object invisible or undetectable. It simply confuses the signal so that the area detected is not the true point of an object. This makes it easier for aircrafts to avoid missiles and such because if an enemy is firing at a point that appears on their radar, that point is not actually the point that the airplane is existing in because of its stealth mode that's confusing the signals. So cloaking is extremely similar, except that the main goal is to make an object both invisible and undetectable. So instead of just having the radio waves redirect the signal, it's supposed to kind of have the radio waves be undetectable from basically the rest of them. It's not supposed to have any differences. So there's been a lot of clever inventions that have contributed to the advancement in cloaking technology, but complete coverage is something of the future. In the most recent addition to the cloaking world is an ingenious invention by a professor at the University of Rochester named John Howell and a graduate student, Joseph Choi. So basically, what they did was they used several lenses to effectively bend visible light around an object, thus making it invisible to your eyes. So viewers cannot see the object behind the clear lens within a 15-degree radius, which is the largest amount of leeway that a cloaking device has been able to achieve so far. So in their paper on the Rochester cloak, which is what they call it, the duo says, in order to both cloak an object and leave the background undisturbed, the researchers determined the lens type and power needed, as well as the precise distance to separate the four lenses. To test their device, they placed the cloaked object in front of a grid background. As they looked through the lenses and changed their viewing angle by moving from side to side, the grid shifted accordingly, as if the cloaking device was not there. There was no discontinuity in the grid lines behind the cloaked object compared to the background, and the grid lines matched. So basically, Howell and Choi have even come up with a formula that can be used to calculate variables that you would need to know in order to make different size cloaks or cloaking devices. So they came up with a formula that has variables such as lens size, distance, instances, like how many magnifying glasses or lenses. And there's even instructions on how to make your own cloaking device on the University of Rochester's website. So honestly, could you imagine if these new lenses were shrunk down and placed side by side? They could form sort of a wall of light bending lenses. So that could really make something invisible, but so far it hasn't been done yet. So other forms of cloaking have previously been invented, each one improving on the last. For example, according to ArmyTimes.com, a coating was invented in 2006 by Boubacar Kanté, but it only worked on microwaves and in 2D. New advancements have incorporated the use of Teflon, a super strong hydrophobic synthetic material. It's also the stuff that makes your pans nonstick. So they also added ceramic cylinders, and the new product is 10 times thinner than the one from 2006, and it can also intercept waves that are 1/10 of a wavelength long, which making it possible to deflect visible light. But the problem is it's still only at the 2D level. So basically this would mean that you would need to look at the object straight on in order for the coating to work. So once again, angle limitations are a major problem. The experiment tested the newest cloak with light hitting at a 45-degree angle, and it only works effectively within a 6-degree range of angles. So compared to the Rochester cloak, which works within a 15-degree radius, the Rochester cloak kind of wins in that form. But then again, the Rochester cloak only works with visible light. So you can cloak any kind of wave, really. You just need to figure out how to manipulate it. But in order for something to be truly undetectable, you would need to cloak all forms of electromagnetic waves. So that is very challenging. So basically, honestly, the possibilities are endless with cloaking, and the revolution has just begun. So, thanks for listening or watching.